As the programs you write grow in complexity, and you start to make use of data structures which can expand or shrink over the course of your running program, it helps to have access to dynamic memory, also known as heap space, which is what we're going to be looking at in today's video. Let's begin by contrasting this with stack and static memory, which we've looked at previously. So stack memory is automatically established for you or allocated for you when function calls occur. Right? So the compiler is setting up all of the instructions and doing the bookkeeping to allocate some space for your local variables and your parameters, and then free them up when your function calls return. There's some useful qualities to stack memory. The biggest one being that you don't have to worry about all of these steps. Once you understand the semantics of how the compiler is going to establish a stack frame and give you some isolation, you can depend on that without having to really think about it. It's an abstraction that the compiler provides to us as programmers. The other big upside is that the frames are going to have some protection from one another. And so you can have multiple frames to the same function call living on the stack at the same time. And this is true when you have a recursive function, and you can have many function frames, each with its own space and each with its own local variables separate from one another without there being any problem. And this is really nice for ensuring that you don't have to worry about the names of the variables that you choose local to one function relative to another. And that's an even more common form of protection and a bigger upside in many cases than just the ability to have many frames of the same function on the call stack. There are some downsides to stack memory, though, that we should remind ourselves of. So for example, the lifetime of stack memory, or memory that was allocated when a function call occurred, that memory expires as soon as that function call returns, right? Or as soon as the memory that was allocated in a nested scope, as soon as that scope closes, right? And so the lifetime is established and controlled automatically for you. You don't have control over how long a local variable sticks around, other than knowing that it's going to stick around until that function call returns. Another downside is that you can't, in the C programming language, pass an array by copying it. Remember, our array names are just aliases for the first byte of an array, and then we're effectively doing pointer accessing and manipulation in order to work with an array. And so there's no way to return an array from a C function call, and what we wind up needing to do is pass a pointer into another function that gives access to some array that was allocated in the outer or the calling function. So working with arrays is kind of awkward when you need variable amounts of data, and unless you're very careful and deliberate in how you go about this, it winds up being difficult to pull off. So there are some downsides to stack memory. Let's look at static memory and compare and contrast its pros and cons as well. So static memory is fixed in size when the program is compiled, right? So as soon as you compile your program, which, remember, for a compiled program that's distributed out in the world, that can mean you compile it once and then it's out on the App Store, and every time someone downloads it, it's the same version, the exact same compiled version that you made as the developer. And so the idea that the amount of memory that's allocated for static storage space is fixed in size at compile time is a problem, because you often want, when your program is out in the real world, there are many problems where you need to grow the amount of memory that your programs need in order to do their jobs. So there are some useful qualities here. One of them is that the lifetime spans the entire duration of the program, right? We know that the static memory space is automatically allocated to 0, and we can have constants that are loaded as soon as the program runs into our static memory space as well. And we can access that at any point in the program's lifetime and know that we're going to have a valid memory access. We don't have to worry or reason about the lifetime much more closely than that. This is pretty efficient because this all happens as soon as your program loads, right? As soon as your program loads, all of your static memory space is set up and you're ready to go. But there are some limitations. So if you want a program that can handle a wide range of data sizes and you only had static memory, well, you'd have to compile for the largest problem size that you might be able to want to take on. And that would be very wasteful if you knew that you needed to take on a very big problem or data set and you needed to allocate that every time your program ran in static memory. You'd be wasting all that space for the 99 percentile of times that your program runs and doesn't need all of that space. For machines that have varying amounts of memory, which they of course do, you're limited to, you kind of want static memory to take up as little space as possible so that it can run on the widest range of machines. Because if you compile a program and it requires more static memory than your machine has available to it, which would be pretty rare for a general purpose computer program, but when you're working with embedded systems, this might not be as, this might be more constrained than you would expect. An embedded system being something like an Internet of Thing device, a little Arduino, these little chips that you can write C systems programs for, have much more limited resources than a full-blown laptop or desktop computer. And so if all you had access to was static memory, you would typically try and shoot for the smallest amount available to allocate and make use of in order to run on the widest range of machines. And notice how there's this tension here between, well, that means that like the size of the problem that you can store in that area of memory is going to be small, but we really want to be able to take on a wide range of problems. So enter the solution, which is sort of the Goldilocks of these two, which is dynamic memory. So it's going to have some pros, which are going to make it more appealing in some instances than either stack memory or static memory. But we'll see that there's also some downsides as well, and that it's more work for us to use. Dynamic memory is allocated as your program runs. So in a very similar sense to stack memory, right? So stack memory doesn't get allocated until your program is in motion and in process. Same idea with dynamic memory. You are in full control in a systems language like C, C++, or Rust over the lifetime of the memory that you're allocating. And this is different from automatic memory and static memory, right? The compiler decides for you the lifetimes of those two things. With dynamic memory, you have complete control over this. And dynamic memory is going to be safe after you allocate it. And we're going to see that that's an explicit step that we have to take on. We have to say, hey, system, I want, this many bytes of memory from the dynamic memory space, and you'll get back a pointer to it. And as soon as we get back that pointer and initialize that memory, then it's safe to use and the lifetime has begun. We're going to see that, well, we also have to tell the system when we're done using it. And this is going to be completely unrelated to scope, right? So when we're done using it, we'll say, hey, free that memory back up. You can use it for whatever else you want. I'm done with it. And so we're going to be in full control over the dynamic memory our programs use. This is great because our process can then request more memory as it's working on a larger and larger problem. And the amount of memory that our program allocates can scale to match the size of the problem or the size of the data structures that it needs to work with on demand and dynamically as the program's running. And the operating system's happy to do this until it can't, until we run out of memory. And there are ways of writing programs that run out of memory and the operating system will crash that program. So where is dynamic memory actually located? Well, it's above static memory, and the space in memory is typically referred to as the heap. And heap space will grow up as we allocate more memory and tends to grow towards the stack and in the direction of the stack. Now remember, in a modern machine, this is a 64-bit address space. So the gap between where the top of the heap is and the bottom of the stack is, if we're thinking about the stack growing top down, is insanely large. And there's a huge amount of space there. But in older systems, it was such that when you were very memory constrained, or if you're in an embedded system with very little system memory, these two things can collide with one another. And that collision, when your stack frames grew to the point of interfering with your heap space and they would overwrite each other, that was the original variation of what a stack overflow was. You're overflowing your heap space or your static memory space if you weren't making use of heap space. And that was the original source of what the stack overflow error was. Nowadays, a stack overflow, there's just so much memory in your system. It's typically a stack overflow is going to be when you overflow just the stack segment, which will be much smaller, and you would never actually reach the heap from growing your stack in that way, like on an infinitely recursive call. There are limitations though, and these are pretty significant concerns that we need to be very careful about how we go about working with dynamic memory. The key limitation, or the key downside, I should say, it's not really a limitation so much as it is an extra responsibility, is that you're responsible for the lifetime of memory that you allocate in your program. And this is new. Previously in languages like Java or Python or JavaScript, you haven't had to clean up after yourself. When you've allocated new objects and new arrays on the heap by using the new keyword and getting a reference back, which is just a pointer, when you're done using it, you didn't have to do anything special. The system took care of freeing that memory back up for you when you were no longer using it. And there are some clever ways of knowing that you could no longer use it because there's no way for you to use it. And that process is called garbage collection. Well, in a systems language like C or C++, it's on us as the programmer to free the memory that we use, or the memory that we allocate from the heap space. And so this responsibility is a big one. We also need to be careful about the way that we free this memory. We can't free something twice. We can't use something after it's been freed, even though we'll still have access to it through a pointer. There's lots of concerns that we're going to see that we need to be very careful with when we're working with dynamic heap of memory. And so we just need that careful consideration in order to avoid introducing bugs and new kinds of bugs that you've never had to worry about before. When you're working in a systems language like C or C++, there are just new classes of bugs that we'll talk about that you'll need to be aware of and watch out for. So with that, let's look at how do we actually dynamically allocate some memory with the system call, the famous system call called Malloc. So Malloc is short for memory allocator. And if you open up the web documentation for it, see if I can get that to open. There we go. The link in the slides will take you to some standard documentation on this particular system call. So we see that this returns to us a void pointer, which a void pointer in C doesn't mean nothing. It means a pointer whose type isn't being specified. So there's no specific type associated with this pointer. It's just a memory address, and it's on us, the people using Malloc, to know what type of pointer this actually should be, and typically, in some cases, to cast it to be that specific kind of pointer. So that's the return type, where we see that Malloc, when we call it, it's going to give us back and result in a pointer. And that pointer is going to be to some space in the heap that we just allocated, hopefully. And then the size t is a special type defined in standard library that is system dependent, but as long as you use size t, you're guaranteed to be working with valid sizes for your system. On a 64-bit system, this is going to be a 64-bit integer, and this is how many bytes of memory we want to allocate in dynamic memory or in the heap space, right? In the description, you can read a little bit more detail about what's going on, but we're actually going to try and work with this directly. What I want to point out, though, is very careful. Something we need to be very careful with is the return value. So notice that Malloc will return a pointer to the allocated space. But if a null pointer is returned, then the system was unable to allocate the memory that we were requesting, and we need to error out in that case. So we're going to look at an example of how we do this. All right. So let's actually jump into some code, and I would encourage you to pause the video here, get open one of our container sessions, and we're going to jump right in. I went ahead and made a folder or a directory using makedir for this lesson. And I'm going to go ahead and open up a file named vim heap memory.c. All right. And I'm going to go ahead and include standard.io.h, include stdlib.h, and I think that'll be enough for now. The Malloc function is defined in the standard library, stdlib, and is typical of any POSIX, which is Unix standard system. So I can go ahead and set up a main function, And let's set up two helper functions. So one is going to be a function that returns to a string. So our first examples here are going to be working with dynamically allocated string values or character arrays that we store in the heap. And this will simulate a little bit of what a language like Java is doing with all of its string values in the heap. So we're going to have a function named string malloc, and we're going to give it a size t, which is the number of characters this string should be able to hold. And let's go ahead and set up one more forward declaration for a function that will pre-populate the string or pre-populate an array of characters if we give an address with the lowercase alphabet. All right, so we're going to have, this will be a void function, and let's name this fill lowercase. And what we're going to give it is a character array that is a string, right? And let's actually, for good measure, let's give it a pointer to a character array, and then let's go ahead and also give it a length, so a size t length. And if we're thinking about this, we should assume that the filling some lowercase character array, that there should be at least 26 values in it, but it's always good practice whenever you are, writing a function in C that is going to have a side effect of writing data back out to some pointer that was handed into this function, right? So in this case, the point of this function is going to be to modify the array of characters named stir, whatever we give the first address of this array to, and then we're going to do that up to some length. And by giving an explicit length, we're putting the onus on the caller to be sure that they allocated and have enough space here. Whereas if we depended on there being a null character at the end of this string, and we didn't give a specific length here, we might open ourselves up to what's called a buffer overflow error, which is a security concern. And for more on that, I would encourage you to take a course on deeper security. But effectively, wherever there's a buffer overflow, you potentially introduce the ability for some hacker or a nefarious actor to influence your program and take over it and start to run whatever code they want on your machine. So that's the concern of a buffer overflow. All right. So let's go ahead and fill in this void fill lowercase helper function just to get it out of the way. And char stir size t length, right? And all this is going to do is for int I is 0, I is less, and actually I'm going to make this a size t because we're giving a size t for length, size t I, while I is less than length plus plus I. And what I might go ahead and do is, because we want this lowercase to only go up to 26, I might just say length is assigned the if length is greater than 26, length is assigned 26, right? So this is just sort of a little bit of a guard. And now what we're going to do is say, okay, stir at index I is assigned, we'll just use some ASCII arithmetic here, the character A plus I. And then the last thing that we want to do is say, actually, I'm going to change this to 27. And I'll talk about why in just a second. We want to make sure there's room for the null character to terminate this string that we're filling in. And the length here will be length minus 1. Okay, and now let's go ahead and say stir at index length is assigned null character. And this should be length minus 1, actually. Great. So we do I is less than length minus 1, which would be length minus 2 is the maximum value of I for this loop. And then we're saying the very last character in this string is going to be the null termination character. If we gave a length of like 8, we would only fill in A through H or whatever is the 8th letter, and so on. right? Great. So we've got our fill lowercase, and now let's go ahead and set up this, what is really the emphasis of this video, which is let's talk about malloc and dynamic memory allocation. So we have a character string. This function is going to return to us a pointer to a character array, and that character array will be on the heap. And this is a function named string malloc, and we give it a size t, named size. All right. So the first thing we're going to do is sort of prepare this function for its ultimate purpose, which is it's supposed to set up a character pointer, and we'll name this stir, and it's going to return stir, right? Well, what are we initializing this string to? Well, let's go ahead and use malloc to say malloc, and then size is the number of bytes we want. So we're going to be thinking in terms of 1 byte characters, and we're asking malloc, hey, allocate this many bytes for this many characters, right? So if the stir, if the pointer returned to us from malloc is equal to null, we need to be very careful here. And what we're going to do as a matter of just an idiom in this course is we're just going to exit out. We're going to print an error and exit out. So we're going to use fprintf, and we're going to print to standard error, and the message is out of memory, right? This fprintf function call is very similar to printf. The key difference is we give a specific, what's called file handle as the very first argument. And standard error is an output stream for if our program is producing errors while it's running, that's where we should be writing those errors to. And this is contrasted with standard output, which is where we would normally print regular intentional output to. When we get to talking about file IO or IO a little bit more specifically, we'll spend some more time distinguishing between standard out and standard error and talking a little bit more about the implications. For now, just know that if you want to produce an error message in a program in C, this is a more conventional way of doing it. And then what we're going to do is we're going to exit the process with an with a failure status, exit failure, which is a constant that I believe is bound to the value 1 to say that this process, when we exit with a status code of 1, it's a unexpected result, and we're going to go ahead and know that the operating system knows that this is a failed program run for whatever reason, and us as someone using this program could inspect, did this program exit normally or did it exit with a failure? And we'll look at that distinction when we get to scripting in a little bit more detail. So we're also going to set up all of let's go ahead and zero out all of the bytes in this particular string so that it looks like every byte in this string is 0. So I might have a size ti that's initially 0 while I is less than size, and plus I, and go ahead and say string at index I is assign the null character. All right. So we've got a malloc, a string malloc function that is going to, we give it the number of bytes, the length of the string, and we're going to have to be sure to remember that we need to leave 1 byte for the null terminating character. That'll allocate some space on the heap dynamically and give us a pointer back to it. If for some reason the system didn't have enough memory to do that, the program will crash. All right. And so if we wanted to try actually using this function, what we can do is say, okay, let's set up a char pointer that we can name stir. And I want to remind you something that's hopefully second nature at this point, but the fact that I'm choosing the name stir in all of these different places is a coincidence. This could have been a_stir, and again, these are local variables, so the names are independent of the other frames. And we're going to use our string malloc function, and we're going to say, okay, let's add, the alphabet has 26 letters in it. We need 1 for the 27th letter, so we can go ahead and set up 27. But that's a magic number, so why don't I go ahead and define alphabet length to be 27. or sorry, 26, right? And so when we malloc, we can say alphabet length +1. And that +1 is for, the null character. And using strings and thinking in C and realizing that a C string always needs the space for that null character, it's no problem to just add 1 onto that named constant. So now we can fill lowercase the string and go ahead and print it out. So printf %s is the printf formatting specifier for printing out a string, and we're going to print out str. All right. Right, and so we needed to give a length to fill lowercase. Well, this was a length including the null character, so we can also say alphabet length +1. All right, so this will fill in all 26 of those characters. All right, so we've got a program, and it's something pretty straightforward at this point. We're allocating some memory for a string. We're filling it in with lowercase letters. Let's go try GCC W all, W extra, standard C11. And I'm not going to give it a special name. We'll use a.out for the binary name, and we'll compile this with debugging flags. So with G and heap memory.c. And now let's try running this program. And what do you know? We get A through Z printed, all lowercase, and we used some heap memory, dynamically allocated memory, to do this. What I want to point out as particularly interesting, and this is an important thing to recognize in this example, is notice we allocated how the size of the string that we needed in a function, and then we returned that value, a pointer to that string, back to some caller. So this is an example of something that we couldn't do if we tried to set up an array without using some clever techniques that are very modern C appropriate. We couldn't dynamically allocate an array here and then go and return that array back to the caller in the way that we're doing in the same way that we're doing here, because the lifetime of a stack value would be as soon as this function returns, that array that was allocated in this function call, disappears, goes away, or is considered reclaimed. But here we're saying, no, operating system, give me some heap space, and heap space we get to control the lifetime of. And the operating system says, okay, here's a pointer to the heap area that you can have access to. And we went ahead and nulled everything out, and we returned that pointer back to the caller. And so now the caller has access to memory that was allocated in a function that it called. But now the caller is going to be responsible for the lifetime of this allocated memory. And we should probably think, well, we didn't do anything special here to free this memory up. Do we have a memory leak? And is there some way that we would know whether we would have a memory leak? Because we allocated this space in the heap, but we never freed it, right? And what I told you earlier is that we have to free it. It's on us to do that. So how do we know whether or not our program has a memory leak? Well, there's a tool named valgrind. And it has that can do a lot of things. It can profile your programs to let you know how much time is being spent in certain functions. It would give you a sense of what functions should you go optimize. But it can also check for memory leaks. And so what we're going to check is we're going to use the full, which for the types of programs that we're going to write, which are pretty straightforward little systems utilities, this is totally fine. So we're going to have the full leak checking, and then we give the name of the function, or the name of the program that we're trying to run. So we run our program, and it gives us a summary of whether or not our program had memory leaks in it. And notice that it definitely lost 27 bytes. So we allocate it, and that aligns with our allocation, right? We said, hey, give us 27 bytes. That's 26 for the alphabet, 1 for the null character. And this was in one block. When you start having many different allocations, you might have multiple blocks of memory that are given to you by the operating system. If we look up a little bit, we can see that the place where this happened was the in Malloc. So this memory was allocated by the Malloc function, but this is giving us a call out or a trace of the call stack where this memory was allocated. And in string memory, or sorry, in string Malloc on line 18, that was where we called Malloc and where this allocation happened that was never freed. So we need to free our memory. Well, there's a corresponding function call that we'll see in this next slide called free that says, hey, I'm going to give you the pointer that you gave me back that says, here's sort of my lease on this particular segment of memory. And I'm going to give this pointer back to you for you to free this memory. And I'm going to promise to you I'm never going to use that pointer again unless I called Malloc and for some reason you gave me that same address back. All right. So we need to go clean up after ourselves. And the slide has a set of steps for checking whether or not you have a memory leak using that same tool we just looked at. Before we even use a tool, the other way that we can tell whether or not you have a memory leak, and you can kind of desk check your code without even running it or using a tool, is you can say, okay, is there anywhere in your program where you have a Malloc, or we'll see there's another call named calloc that's very similar, where you have a Malloc or a calloc, is there a corresponding function called a free? And in this program, there's no call to free, so we know that there's already, like that's something that's going to tell us that we have a memory leak. So the question is, when do we want to free this memory? And where might we put that call in? Well, ultimately, we're allocating some memory in main, assigning it to this string variable, and we're printing it out. So maybe after we print it, that's when we're done with it. So we say free and then stir. And we say that free command is saying, hey, you can reclaim this memory. You can use it for whatever you'd like. I'm done with it. You don't have to do this next step, but I'm going to encourage you to always, after you free a particular pointer, go ahead and assign it a null pointer. And the reason for this is because we're controlling the lifetime, right? We don't want to access that pointer again. And if you tried to at some point say, dereference stir, or if I can actually give you an example of this. We're going to have 3 printf statements here, right? So notice the first one is after we fill lowercase, then we're calling free. We're saying, hey, reclaim this memory. I'm done with it. And then we're going to printf again with that same pointer and try and print out what that memory address evaluates to. And then we're going to change that pointer to be a null pointer. And then we're going to try and print it out a third time, right? So if free, if this were, free is when technically the lifetime of the memory that stir points to expires. So we should never actually use stir after free, right? That's one of the key takeaways from thinking about the lifetimes of dynamic memory is after you free it, you should never use it again. But here we are using it again, and let's see what happens. And then we're assigning null to it, and that's okay because we're not actually assigning null to the heap space, right? We're saying the local variable stir, which is a pointer to a character, that's no longer going to point to somewhere in the heap, which we said we're done using, right? We're saying that's just a null pointer, and we're never, if you try to dereference a null pointer, our program's going to have a segmentation fault. So if we tried recompiling this, and I'm going to go ahead and add the ... Oops, I'm off my screen here. Apologize if that was... Hopefully that didn't cause anything to go off the bottom earlier. But we've got our command here, and then I'm going to go ahead and run my program after that. So I just used the double ampersand, which said if we successfully compiled, then go ahead and run a.out. And notice in this compilation, we get A through Z, and then we get an empty line, and then we get a segmentation fault, right? I'm going to try recompiling this without debugging symbols, and I'm actually going to use, let's see. So this is actually encouraging to me that that we're not seeing A through Z again. That means that when we called free, the free implementation that we're using is at the very least putting a null character in at that point in memory. But notice that the program didn't crash. And sometimes because we're reading from memory that hasn't, that its lifetime is expired, and when you read from expired memory, you get the behavior is undefined. You can't actually depend on that being anything useful. And you should probably expect it to crash or hope that it crashes, but notice that it didn't crash here. It just printed out an empty line or an empty string. So that actually feels good that we didn't see the same memory contents there before. If we had more mallocing and freeing that happened between those steps, the memory allocator is allowed to reuse that same space. So there may have actually been data put back in there, and we may have been able to read it at that point in our program, even though we shouldn't have. And so the reason why we encourage always nulling out a pointer as soon as you free it is because it's a much better behavior to get a segmentation fault for trying to read a pointer to some dynamic memory that you've allocated after you freed it than it is to not get a segmentation fault. With a segmentation fault, your program crashing, that gives you something to go and debug. Whereas if you don't crash, you're going to have some really weird, funky behavior that's hard to debug and confusing to track down until you use a tool like Valgrind or something to dig in a little bit deeper. All right, so as a matter of best practice, when you free dynamic memory that you're no longer using, the very next line, just go ahead and assign a null, the null memory address to that pointer value. All right. Did it matter in this case? Was this a big deal? Yes and no. And the yes part is what I want to focus on. Yes, this is a big deal because it's so easy to, we're having to develop new habits when we're using dynamic memory in a systems language. It's so easy to develop bad habits and to forget to free. And that can work for small, trivial programs like we just saw. But as you start writing bigger programs, if you have memory leaks, eventually your program will run out of, or your process will run out of memory space and you'll have a crash. And that's really hard to debug as well. So it's best to get in the practice of practicing good dynamic memory hygiene and always cleaning up anytime you've allocated memory. The no part of is this a big deal as well, our program exited just after that. And as soon as your program exits, any memory that the process was using gets reclaimed by the operating system and things are okay. Right? So in this exact example, it didn't really matter, but you should pretend that it does and behave as though it does. And we're going to grade as though it does, right? We're going to be looking for no memory leaks as we move through the rest of this course when we're working with dynamic memory. All right. So the lifetime of dynamic memory is it's safe to use after you've allocated it and initialized it. And it's unsafe to use after it expires when you free it. And so you can only use it between those two bounds. But notice that this lifetime is now completely unrelated to scope, right? Because we can allocate it in one function, we can return that pointer to another function, then it's free to do whatever it wants, and then some other function or that function can free it. And it's going to be on us to decide when we allocate and when we free in our program. So we're going to have complete control over the lifetime. And that's different from scope, where scope, that's set up by the compiler and the structure of your program. We just saw an example where we tried to read what the contents of a pointer after we freed it. And so notice that pointer, we still had access to that memory and it was still in scope, but that memory that it referred to had expired. And that's the key concept to wrestle with. And I would encourage you to pause the program and reflect on that for a moment. After you freed a pointer, that pointer hasn't changed. Its value hasn't changed. It still refers to some memory address in the heap. You can still use that variable. You can still refer to it. We assigned a value of null right after that. So that variable is still in scope. It still has the same value, but we can't treat the memory that it refers to as valid anymore because that memory has expired. We've said, hey, we're done using this memory space. You can have it back to use as you want, system, so that if I needed to allocate more memory in the future, maybe you'd give me back that exact same space. And this is why we assign a null pointer after the fact, so that if we do try and use that pointer again, while it is in scope, we'll hopefully get a segfault. When we're working with array-like memory, we actually tend to want to use calloc instead of malloc. And in this past example, we started with malloc and we allocated a memory or a character array. But we probably should have used calloc. And if we wanted to show an example of a better practice when thinking about allocating an array of memory in C, we're going to take a look at the calloc function in this next example. So when would you use malloc? Well, when you're working with structs or when you need to box an individual value on to heap space so that you have control over its lifetime. In those two scenarios, you would use dynamic memory and allocate it with malloc. When you're working with an array, you should probably use calloc instead. So let's go ahead and try adding an example of calloc to our file here. So character array, string calloc. And we're once again going to just give it a size t size as a parameter. Okay. So this is the declaration, same exact signature except for the name. It's also going to give us back a pointer to the first byte of a character array in dynamic memory. For the purposes of trying to keep as much of this example towards the top of my file, I'm actually going to go ahead and define it below main and above string malloc. But if you wanted to do this below string malloc, which would probably be a better practice since that was the, I can reorder those two lines at the top. I'm going to go ahead and say character pointer string calloc is the function we're defining, size t, size, and we're ready to go. Okay. So this function is going to look very similar to malloc with a few subtle differences. So the first difference is we're going to be using the calloc function call. Oops. And so this is another system call built into stdlib.h. And what calloc is going to do that's different from malloc is malloc we give the absolute number of bytes that we want to actually make use of. With calloc, we're going to give the number of elements we want in our array, and then we're going to give the size of an individual element in our array. Okay, so the number of elements is size, and then because we're using a character here, and we could do size of char, right? Now that could have been just one. We could have written just one there, but this is a little bit more explicit and it will compile to the exact same code because size of is a built-in operator. And we're going to ultimately return this pointer, right? Now, just like with malloc, we need to be sure that this call succeeded. And the way that we'll know whether or not this call succeeded is whether we get a null pointer back. If we got a null pointer back, we're out of memory. So let's go ahead and add that same check as before. So if the str pointer is null, then what we're going to do is print to our standard error the message out of memory and exit with exit failure. All right. One of the key differences between calloc and malloc is when we use calloc, it's going to automatically initialize every element, every byte in this space to be zeroed out or nulled. So we don't need to do anything else. This is already set up as a valid value. It gets returned back and we're good to go. All right. So now that we've got this example, we could change our original call here from string malloc to string calloc instead and convince ourselves that this will still work. So I've changed my call from calloc or from malloc to calloc, and now I'm going to go ahead and use it. Looks like we're doing fine. If I wanted to do a leak check using valgrind, and I actually forgot to go ahead and prove to ourselves that we fixed our leak before. After we freed, notice that it says in use at exit 0 bytes of dynamic memory, and so we made 2 frees in that time. And you'll see that even though in our program there's only 1 alloc and 1 free, as long as there's a matching number, it's okay. Those were happening from something outside of our purview. All right. So we've seen calloc and malloc, and we've seen how to free a pointer in memory after we're done with it. And that frees up the allocated space in dynamic heap memory. What if we wanted to use more space? What if we needed a segment in dynamic memory that, well, we started with one copy of the alphabet, all lowercase. What if we wanted to have an array that had 2 copies of the alphabet, all lowercase? Initially, we only allocated 27 bytes. That would mean we would need to allocate 53 bytes for A through Z, and then the null character. And when we're working with arrays on the call stack, we know that we can't resize an array on the call stack. It is whatever size it's initialized to. In static memory, we can't resize anything that's static. That's baked in at the point of compilation. Well, with dynamic memory, we actually can ask for more space. So we can say, hey, I had this allocation that was 27 bytes originally. Now I want that and same allocation to be 53 bytes. How would this work? Well, in some cases, that can be done in an efficient way. If there's nothing stored after it and the system knows and it's clever, it might say, okay, I've just given you that much extra space. It was right at the end of what you already had allocated. And here's the pointer back to the first character. It hasn't changed. It's still the exact same pointer. However, there's no guarantee that when you called alloc again and the ordering in which you're saying, hey, give me some more space, and now resize this thing. So sometimes there might be multiple arrays back to back to back. The more general way that you would understand asking for more space to work, in the way that you kind of have to assume this is how it's going to work and behave as though potentially the actual address that your contents are in have changed, is this process on the slide where imagine you've got an array and you want more space for that array, but there's something right next to it or something right at the end of it. There's another array. So you can't just expand it. Well, what do? Well, the call that we're about to see, what it will do is it will say, okay, well, let's just allocate however much space you need somewhere else. And we're going to copy all of the original data from the first allocation over to the new allocation that has all that space you're asking for. And then we're going to free up the space that you'd previously been using. And lastly, we're going to return to you the very starting address of the new storage space that's been reallocated and that your data has been copied to. And so even though that's a little bit less efficient, it's significantly less efficient because you're having to copy all those bytes each time you reallocate. It is how you need to assume that the call to realloc is going to work. In some cases, it will be more efficient. It'll just expand your allocation and no change to the address that you get back. But in general, we need to assume that we're copying everything else out, or everything in the original allocation out to some new space that's got more space. The old memory address will have its lifetime expired, and the new memory address that will be returned to us is going to be what we assume to be our memory working moving forward. All right, so let's try adding to our example here and going ahead and defining a string realloc, char string realloc. And the way realloc works is we need to give it the pointer to the first byte of our memory allocation. So this is going to be a char original. And we're going to have a size t desired length. So this will be the, maybe I'll call this new length, right? And I'm going to go ahead and for purposes of illustration, just define this at the top of my file here, just below main, and say, okay, character pointer string is what this will return. It will return the address of the first byte of dynamic memory that we're reallocating to. We're reallocating, and this is going to have the original string pointer and then the size t for our new length. All right. So for reallocation, we don't need to declare a new variable. We could if we wanted, but we can just reuse the idiomatic use of this function realloc. So the system call is named realloc, and we give it the pointer that we're reallocating and the new length. Right? And ultimately, we're going to return this. Just like with Malloc and calloc, realloc also needs to be tested to be sure that there's no null pointer return. So if original is equal to null, that means we've run out. You know what? I'm just going to go down and use my Shift V for block mode or line mode in Visual. Select both of these lines, press Y to yank, go up to line 23 and press P to paste it in. All right. So this line 22 is the one that's the most important. And what this function called realloc is saying, hey, I'm going to give you a pointer, which is original, to some dynamic memory address that I previously allocated. And I'm going to tell you how many bytes I want you to allocate for me. I want you to move, if necessary, allocate a new memory space that has new length number of bytes if you need to, and copy everything over to that, and then just give me a pointer to that new space and go ahead and free up the old memory address and consider that memory that you can reuse if needed. And so realloc returns a pointer to the new allocation. And again, in some cases, this pointer might be the same pointer, right? Because realloc might have been able to just expand the allocation and use the same starting memory address for the very first byte. But in general, you can't assume or plan, or you should assume that that's not going to be the case, and assume that original is probably going to be a different address, and just assume that it is a different address, and that's okay. Realloc goes ahead and frees the old memory, and now you've got to take care of freeing the new address. So we return original, and let's see what we can do here. Well, we printed just the lowercase, so let's go ahead and try reallocating strings. So we can say string realloc, and I should say that, again, we are trying to keep track of the pointer that it returns. We don't have a guarantee that it'll be the same thing as what it was before. So string realloc, and what are we reallocating? We're reallocating the string, and what are we trying to reallocate it to? 2 times alphabet length plus 1. Right? And so again, that plus 1 is for the null character at the end of our C string, and we want to be able to store 2 copies of the alphabet. And so now we should fill lowercase. And what is the pointer that we're giving? Well, we've already filled in the first half of this string, right? The first half of the string is already A through Z followed by the null character. And that null character is going to be at index 26, right? Because A is going to be at index 0, Z will be at index 25, index 26, which is the 27th element, would be the null terminating character. So we probably want to give the address of this string at alphabet length, right, which is 26, as the starting point where, hey, this is where I want you to start writing A. This is a memory address. And notice we're able to pass in a pointer to the middle of an array. And that's kind of cool. That's something that you've never been able to do before in Java or any other language like that. So we're actually giving the address of the middle of some array named string that's stored in our heap space. And we're going to say alphabet length plus 1. Right? So we only need to write 27 more characters, A through Z, and then the null terminating character. And let's go ahead and I'm going to copy line 15, YY, and then P below that, fill lowercase. And let's try printing this out and freeing that string that was that we reallocated. All right. Oops. So I just tried, I didn't actually recompile, so that didn't mean anything. Let me go back up to the options we used to begin with our debugging flags. Okay. And so notice we compile and we run the program, and the first time this prints out, it's just the A through Z. Second time, we have both copies of the alphabet in that same memory allocation. One of the things that we could take a quick look at is the actual memory address of this stir to see if it did change or not. So let's go ahead and print out %p of stir, right? And so the P specifier is for a pointer, and I'm going to copy that and paste this down below. And this will tell us whether, when we reallocated, whether we needed to actually copy this array out to a different allocation and move it, or if the realloc was able to reuse the space and just expand the original space. All right, so I'm going to try this again. And notice that the starting address is in fact different. So this 0x56. And notice that if we were to print the pointer of that we were using on our stack frame, the address of the pointer would be much higher in stack memory. This is in dynamic heap memory, so it's much lower if we were to compare those two addresses, and I would encourage you to try that as an exercise. But notice the starting byte for the memory we allocated on the heap for the first string that we were working with was ended in 260 as its lower order bits. And then we reallocated so that we could have more space. And for whatever reason in the system's library, the stdlib.h, its algorithm said, you know what, I didn't actually set up enough space to be able to do what you're asking for. So I'm actually going to have to set up a brand new allocation, copy out your old information, free up the old memory address, which would have been the heap memory at address 260 lower bits, and then return back to you the new starting byte of this new bigger allocation that you've requested. And that would have already had A through Z followed by the null terminating character. And then the last thing our code did, if we were to go look at it again, was we said, okay, let's just go fill in the back half of this string, right? And so we were able to give the address of an element, at index 26 in this particular range of memory. And the fill lowercase function just moved from there. Notice we only freed once, even though we calloced and then we realloced, and that actually made two different, now that we looked at the pointers here, two different allocations of space in dynamic memory. Well, realloc takes care of cleaning up or freeing any old address that if it needed to move your data and copy it out, it frees up as part of its own subroutine the old pointer or the old allocation. And so we only needed to keep track of, well, realloc gave us back the pointer to the new starting address and we could free it. Now I want to point out something that's very important to recognize. And as you start to work with calloc, malloc, and realloc, you've got to be very careful to understand. And in fact, so the thing to recognize here is that we could have set up a different variable, so char newster. And it would have looked like we could still use this original string pointer because we're reallocating that, right? Or maybe we could think that, oh, maybe we should just realloc, and we've got this handle on this old pointer here in big deal, right? Well, what we saw was this string realloc gave us the new address of where it had reallocated this new space to, and that was different from the original place. And so if we tried to use stir as we are here, we'll actually see a different type of notice that the program doesn't work, right? So it also didn't crash. But if we were to take a look at the output of valgrind and say, hey, is there any problem, valgrind? Notice that we've lost some memory, so we didn't actually free up what we thought we were. And if I were to look up, notice that it's saying invalid free because we were freeing something that had already been freed by realloc, right? And so I would encourage you to think and reflect on why we very much have to say, when we're using something like realloc, be sure that anytime we thought we were referencing to the memory address that was previously at stir, we've got to be sure that we update that variable so that it points to the correct location in dynamic memory. And this is something that you will encounter in as you're working with dynamic memory allocations using realloc. All right. So we've now seen three different fundamentally important areas or segments of memory. And when you're working with values that are variables, and you've got to choose which of these three segments are you going to be working with memory in, and they have different trade-offs. What we spent this video focused on is heap memory or dynamic memory. And the lifetime of memory that you've allocated dynamically on the heap is safe after malloc and calloc. And with malloc, you need to be sure to initialize. And it's expired when it's freed. I should actually extend the slide to say freed or realloc. And so if you use a memory address, you should and you realloc that, you should assume that that address that was stored in that variable is invalid unless the return value from realloc is the same. But what I want to mention, and we'll spend some more time with each of these runtime dangers shortly, is that there are many more dangers that you have to be worried about. There's many more ways that you can run into problems with dynamic memory in a language like C or C++. You've got to check that you're not out of memory. And if you are, your program might not fail unless you actually had a check if the pointer that was returned back to you from malloc, calloc, or realloc is null. Exit your program, print some kind of a diagnostic error message. There are ways that you could gracefully recover from that, but that's a little bit beyond our scope. For now, I think the easiest thing you can do is just fail early and fail intentionally, and just exit that program with an exit status code. You want to be careful not to use memory before you initialize it, because there might be leftover memory from someone who previously used this particular storage space on the heap. You want to be careful not to write beyond the amount of storage space you've allocated. And if you do that, hopefully your program crashes with a segmentation fault, but often that won't be the case. Often you'll have some really hard bugs to track down. If you fail to free memory that you've dynamically allocated, your program will have a memory leak. And for long-running programs, this is especially concerning. If you try to use a memory address after you've set it in the heap, after it's been freed, it's undefined behavior. Hopefully your program crashes, but oftentimes it doesn't. We just saw that we did that and it didn't crash. And then if you double free, once again, hopefully your program crashes. And this means that if you've asked to free the same address twice, hopefully that address crashes. There's some chance that the memory allocator had, someone later in your program, you said, oh, I need some more memory. And the memory allocator says, oh, great, I've got this free space that someone just gave back to me. So I'm gonna give it back to you. And if you've freed that same pointer again, thinking that you were freeing the first allocation and you just did it twice, you would potentially be overwriting or messing up some other part of your program. So the key realization is, because the lifetime is fully controlled by you when you allocate and then free, there's just a much broader range of ways of creating side effects in your programs that you couldn't otherwise plan for, and that you haven't needed to worry about with the call stack or static memory. And so the key takeaways that we'll be practicing as we move forward with working with dynamic memory are: 1, always be sure whenever you allocate that you've got a corresponding free. And 2, be sure that you're checking for a null pointer return back and error out quickly. And 3, this one's the more subtle one that we're going to need to spend some more time articulating. But you want to be sure that you don't keep a lot of different copies of pointers to dynamic memory around in your program in places that you don't need them. And you should typically only have one variable at any given time that's considered the owner of some lifetime, or the owner of some memory space. And that particular variable should be the one that you wind up freeing later on. And then after that gets freed, you just can't use any of your other references to that same memory address. But we'll get some more time and practice working with those concepts. For now, this is an introduction to dynamic memory on the heap with some of the key concerns when you're working in C with malloc, calloc, realloc, and free.